This is going to be a more quantitative understanding. And we're just going to review some of the things we've already talked about, but talk about how electric field lines have a source and a destination. Okay, so electric field lines are, of course, vectors. They have both direction and magnitude, and the magnitude represents how much force will be applied per unit of charge. Typically, when we're looking at electric field lines, we're looking at a vector field. We're looking at an infinite number of vectors that are distributed throughout space, and they depend on usually some sort of distribution of charge. Here we can see a positive charge where the electric field lines are emanating out of, and we can see a negative charge where the electric field lines point to. In this case, we would call this a dipole because both charges are equal in magnitude but opposite in charge. And again, follow any of these field lines and you can clearly see how they're all pointing toward the negative charge, but yet pointing away from the positive charge. Now, the electric field strength is pretty much represented by the density of field lines. So where we see the field lines very, very tight and compact, that would indicate a very, very strong field between the two charges. Where the electric field lines spread out, there, the amount of, or the intensity of the electric field is much, much less. And again, all electric field lines will start from a positive charge and will terminate at a negative charge. Now, this is going to be revisited later on when we talk about Gauss's law, and we're going to surround a charge with a surface. We're going to, take some type of surface and surround it and show that the field lines, the amount of field lines times the area is proportional to the charge contained within the surface. But again, we can clearly see that where we have positive charges, we have new field lines being generated, and where we have negative charges, those field lines will terminate. So negative charges, field lines will point toward, because any positive charge is going to be pulled in the direction of a negative charge. Thus, the field lines show the direction that the force will pull if the charge is positive. If the charge is negative, it will be in the opposite direction. Again, if we place a positive charge near another positive charge, the electric field lines point away because the force in that charge will also point away. So again, looking at the dipole charge, one thing that we notice is that the total charge of the system is actually zero. If both are equal and opposite in charge, plus Q and negative Q, the net charge again is zero, but we still can have the presence of an electric field, even though the net charge of a system can be zero. Here are two positive charges, and just mapping out the different locations. At A, we would say that the electric field is pointing away in this direction. At B, the electric field is pointing at this direction. Curiously, at C, there's no electric field. Basically, by the superposition principle, the electric field due to the charge on the left and the electric field due to the charge on the right cancel each other out perfectly, and therefore there's no electric field there. This would be an unstable, mechanically unstable spot for another positive charge or a negative charge. Okay, just a little bit of a nudge would cause it to probably slip this way or slip this way in the vertical direction. If the charges are unequal, we get a different shape. Here you can see that we have twice the amount of positive charge as we do negative charge here. So in this case, the negative charge is screening the effect of the positive charge a little bit and canceling out its effect. So again, just a very qualitative discussion here. The positive charges, the lines will point away from them. The negative charges, the lines will point toward them. In the case of an electric charge, some lines will begin and end infinitely far away. Again, the electric field lines are not material objects. They're just pictorial representations of a vector field at various locations. But if we're looking at all the region around a vector diagram like this, there actually exists an electric field at all different locations, and they can be represented by individual vectors. We just use a limited number of vectors to represent them because it would be unwieldy to represent every single point.